Consider a set of point masses connected by linear springs oscillating as shown. We understand this phenomenon quite well, and can describe the system's behavior analytically. We know the system will oscillate at various distinct frequencies, called modes. For example, in this case, we witness the first mode of oscillation. In this case, the second. And finally, the third. These should come as no surprise to anyone even marginally aware of elementary physics. However, if we were to replace the linear springs with less ideal springs, i.e. nonlinear springs, the behavior changes dramatically. Notice that we begin with the simulation in the same initial condition as the linear case. Almost immediately, one notices the evolution of a much more complicated behavior. Moreover, the system seems to move through various periods corresponding to shapes roughly that of the linear modes discussed earlier. Let us slow this down to see the motion more clearly. Initially, the motion almost exactly corresponds to the first linear mode. However, we quickly see the production of a front that whips along the set of points. This front quickly produces higher frequency oscillations that bring the system out of the first mode. These slowly evolve into more complicated patterns, resembling, but never exactly reaching modal motion. How does the system physically evolve? Can we characterize the motion at any given time, or is this evolution effectively random? Enrico Fermi, John Pasta, Stanislav Ulam, and Mary Tsingo, although Mary rarely receives any credit, took up these questions in the 1960s. They first hypothesized that this system would develop ergodically, exhibiting thermalization, a behavior in which the initial modes eventually fade, giving way to an essentially random motion with all modes excited equally. They began by defining a differential equation in terms of the displacement from equilibrium x. Note that although these calculations are performed in the horizontal component, we visualize the system vertically, as the motion is more easily seen in this arrangement. The calculations are equivalent either way. Here alpha is a constant representing the relative strength of the quadratic term. This is taken to be significantly smaller than the linear term. Thus, we can approximate the total energy as simply the kinetic, plus a simple potential term. However, neither of these equations tell us much regarding the overall motion of the system. The one-dimensionality of the problem lends itself to the simple Lagrangian change of variables as shown, where ak actually represents the Fourier coefficient of the kth mode. Since we explicitly pin the system in an initial sine curve, we ignore the cosine terms. Computing the energy in this form yields a pseudo-power spectrum for the system in terms of the kth mode. Thus, by plotting the various modal energies over many cycles, we will not only be able to discern the presence of dominant frequencies, if any, but we will be able to deduce any long-term behavior of the system. Let us analyze this plot in real time. Here we compute the energy of the first 5 modes once every cycle. The energies above the 5th mode never exceeded 0.05 in our system. We begin, understandably, firmly in the first mode. The other energies are approximately 0. This lasts for a very short time, after which we begin to decay into a more complex response. The 4th mode then dominates, followed by the 3rd. The 2nd mode becomes quite clear right about now. With the 4th and 3rd reappearing briefly afterwards. Surprisingly, we return almost exactly to the first mode. This should surprise you. definitely surprised Fermi, Post, and Ulam. The system seemingly exhibits none of the expected ergodic behavior. In fact, the long-term behavior even appears periodic. Overlaying our plot with theirs, we find very close agreement between the two. However, we must point out a few interesting details we discovered in our analysis. First, you will note the Fermi-Post-Ulam plot exhibits energies in the hundreds in their units. Our system only reaches around 1 in our units. Further, Fermi, Post, and Ulam stated they computed the modal energies once every few hundred cycles. As noted, we perform this calculation once every cycle. As such, we see the behavior occur over around 170 cycles, while they see the same behavior over 30,000 cycles. We believe this disparity to be the cause of differing initial conditions. However, we find little to no reason for such a large difference. This remains unexplained. Further, if we consider the energies at every time step as opposed to once every cycle, we note that the energies actually oscillate themselves. The maximal trend traces the same plot as before, but the underlying behavior remains much more detailed. Given the significant technological barrier in the 1950s, Fermi, Post, and Ulam had no way of seeing this small resolution. As such, we are unsure what this implies. Regardless, the presence of a more complicated response suggests the severe disparity between our different scales could arise from how data points are selected. Depending on the frequency with which points are selected and its comparison to this underlying frequency, the long-term frequency could modulate significantly. This too remains unanswered, and we hope to explore the question in further simulations. Additionally, we are curious of the nature of the whip-like front we witnessed throughout, with possible connections to the study of solitons. Even if the front is unrelated, the nonlinearity of the system lends itself to various simulations regarding the behavior of solitons and their effect on the system's motion as a whole. Moving forward, we hope to extend this numeric work to encompass such projects.